Hello, for this review video, we are going to compare the t-test, the traditional t-test of a problem, single variable, that is going to have a sample size less than 30, and compare it to the p-test of the same problem. We should see that we will get the same result, although getting there will be a little different. So let's begin. What we have is a physician that claims that jogger's maximum volume of air is greater than the average adult. This kind of makes sense just because if you do a lot of exercise, you should be able to increase your maximum volume of air your lungs can hold. But is it significant enough to basically reject the null hypothesis that it would be the same as adults? But he's clearly stating that this is going to be a more situation. So what I'm going to do is I'm going to set up my null and alternative hypothesis, and I'll do so for the traditional z-test first. Let me start off with a null, and I'll use h sub 0 for my null, and the average of the adult is 36.7. This was our mu here. And the reason why it's the mu, it's the average of the adults, and his small samples of 15 joggers, this is our x bar. This is our average of our small group here of n sample size, and the standard deviation represented by this letter S is right here. Okay, so our alternative hypothesis is his claim that the maximum volume is greater than the average adult, so it's going to be greater than 36.7. Now we're going to find our critical value, and we're going to find our critical value by looking at the t-chart. Now how we're going to do this is we are going to first of all need our sample size, which is n, or 15, and we're going to go with degrees of freedom, n minus 1, so 14. So we're going to look on the t-chart and the t-chart at that spot to see what our critical value is. Now here we have a t-chart, and this t-distribution chart is based on degrees of freedom. So as we found out, we are going to look at 14 degrees of freedom, and we're going to kind of move along and check to see, based on this table, what our critical value is. Now this is a one-tail test, and therefore our alpha for the one-tail test is 5%. So we need to look in this column here. So we are going to now scroll down from the 5% one-tail to the 14 degrees of freedom until we get right here, which is our critical value of 1.761. So I can now take that critical value and put it right here as this is equal to 1.761. If we find that our test value is greater than 1.761, we will have enough information to reject the null hypothesis. So our step 3 is to now use our test value formula for our t value. And our t value is going to be x bar, 40.6, that's the average of the small group, minus mu, which is 36.7, the average of the population that we're comparing this to, divided by the standard error of the estimate, or the standard deviation, 6, divided by the square root of the sample size, 15. If we do this correctly, we get 2.52 as our test score. Now we can draw our normal curve with 0 in the middle for the average, 0 standard deviations away from the norm. And what this brings us is a critical value. I'm going to put my flag in the ground here at 1.761 and shade in to the right. And now our test value is 2.52, and we can clearly see that the test value is well within the critical region. So since 2.52 is greater than 1.761, you could have also said this the other way, that since 1.761 is less than 2.52, we will reject the null hypothesis. All right, so let's compare this versus the t-test, or excuse me, the p-test. I'm going to want to change colors a little bit here. Now, we can, the first step of the p-test is to use the null and alternative hypothesis. So the null hypothesis is where mu is equal to 36.7. The alternative hypothesis, the mu is greater than 36.7. Now, number 3 from the t-test is actually the second step of the p-test. The t-value is 2.52. Now, the hardest part about step 3, where we evaluate this, is it's a very visual learning process. And I usually call this riding the rail. What I need to do is I need to take my 2.52 at 14 degrees of freedom, and I need to see where that is. So let's go to the t-chart. So here I am on my t-chart, and I'm going to look again at 14 degrees of freedom. Now, what I'm going to do is I'm going to look for that 2.52, and the 2.52 along this line at 14 degrees of freedom. I'm trying to draw it straight so I don't cross off any numbers I want to look at. So the 2.52 is somewhere between two of these numbers. And it would be between this number, 2.52, because that's greater than 2.145, and less than 2.624. Now what I call this is riding the rail, because I'm going to ride this rail up until I get to the one-tail portion. And the one-tail portion puts me here, at this moment where my alpha for this group is going to be, I shouldn't say my alpha, this group is in the top 2.5% to top 1%, which means that this group of athletes is incredibly exceptional to the point where we really should be rejecting or considering the null hypothesis to be wrong. So to convey this idea on the test or final or whenever you have to do it, homework for example, what you should do is you should replicate where that riding of the rail was. It was between 0.025 and 0.01. I usually put a star between the two because our 2.52 followed that all the way up to the star so that you know that that your t-value is between the 1 and the 2.5%. So since your t-value was between 1% and 2.5%, your value, somewhere between the 1% and 2%, is less than 5% and will reject the null hypothesis. Because that's really what we're doing with p-testing. We're checking to see if our actual value percentage is less than the given alpha in this problem, which was 5%, the same alpha over here on the t-test. We can then see if our group is definitely in that top 5%, and in this case it was between 2.5% and 1%, we will definitely be rejecting the null hypothesis. Well, thank you for watching. There's another video to correspond to this page of some of the review guides I've sent out. Please make sure to click that next to get an overview of regression, and also vocabulary words such as the coefficient of determination and what they mean.